Last month, the entire world became fixated on interstellar comet 3I/Atlas as it glided harmlessly past Earth. Yet almost no one noticed the real threat lurking in the shadows. A cosmic giant 100 times larger, designated C/2025 R2, slipped into our solar system completely undetected, concealed within the sun's blinding glare. It was discovered only after its closest solar approach, using a space-based hydrogen imaging instrument. By then, it was too late for ground-based telescopes to sound any alarm. In just 7 days, this massive visitor will sweep closer to Earth than any major comet in recent memory. The danger isn't some Hollywood-style impact scenario. It's what we fail to see and how debris fragments hiding in our blind spots could trigger consequences we haven't even begun to anticipate. How did we miss something this significant? And are we truly ready for what comes next? On September 11th, 2025, a faint ultraviolet glow captured the attention of Vladimir Bizugly. He was analyzing data from the solar wind anisotropies instrument, known as SWAN, aboard the SOHO spacecraft, a vessel that has spent nearly 3 decades monitoring the sun's outer regions. The image revealed a hydrogen cloud expanding in an unexpected direction. Within hours, the SWAN team flagged it as a possible comet discovery. Ground-based telescopes scrambled to confirm the sighting, but the object remained hidden in the sun's overwhelming glare, invisible to every optical survey system on Earth. Only SOHO's ultraviolet sensors, specifically designed to detect hydrogen streaming from icy celestial bodies, could reveal what lurked there. By the time the discovery circulated through official astronomical channels, the comet had already passed its closest point to the sun. Bizugly's find was officially named C/2025 R2 SWAN, marking the 20th comet credited to this aging space-based observatory. Its hydrogen envelope stretched across millions of kilometers, signaling intense outgassing and rapid brightening. For astronomers worldwide, this represented both a triumph of persistent observation and a stark reminder of our glaring vulnerability. Without SWAN's ultraviolet imaging capability, the comet would have slipped past completely unseen until it was far beyond perihelion. Most of the world's telescopes have been focused on the wrong region of sky, blinded by the sun's brilliance. The discovery wasn't the work of a single observer or instrument. It was a product of a system specifically built to detect what ground-based eyes cannot perceive. The question now extends beyond what SWAN is. It's about how many more giants like it might be hiding in plain light. The sun's glare carves out a blind zone that has haunted astronomers for over a century. This region, known as the Hollich effect, covers a slice of sky within approximately 30 degrees of the sun, an area where no ground-based telescope can reliably search for comets or asteroids. During these critical weeks, even the most advanced optical surveys become powerless. Twilight washes out faint objects, atmospheric scattering turns the sky opaque, and the very geometry of Earth's orbit means that anything approaching from the sunward direction remains hidden until it swings away from the solar disk. Between August and mid-September 2025, C/2025 R2 moved through this invisible corridor. From our vantage point on Earth, the comet was buried in daylight, its rapid brightening entirely masked by the sun's overwhelming luminosity. The Hollich blind spot isn't a technological glitch or equipment failure. It's a fundamental limit imposed by physics and geometry itself. Even the largest, brightest objects can slip through undetected if they approach from the wrong angle at the wrong time. Space-based instruments like SOHO SWAN camera represent rare exceptions to this rule. By observing ultraviolet emissions from hydrogen, they can spot comets in the very places where earthbound eyes cannot reach. However, SWAN's field of view is limited, and its aging detectors offer only a patchwork glimpse of the threat zone. The reality is stark and unforgiving. For nearly a month, a long-period comet streaked toward the inner solar system, its outgassing and dust eruptions invisible to every major survey system on Earth. The Hollich effect doesn't just hide the faint and distant. It can cloak giants until they're already among us. Each object lost to the sun's glare serves as a reminder that our cosmic watch has blind corners, and that the next warning may arrive only after the danger has already passed. On September 12, 2025, C/2025 R2 reached its perihelion, its closest point to the sun, swinging in at 0.503 astronomical units, or approximately 75 million kilometers from the solar furnace. This is the moment every long-period comet both dreads and cannot avoid, the instant when centuries of cold storage end, replaced by a surge of solar energy that can transform a quiet traveler into either a spectacular show or a cosmic casualty. At this distance, the sun's radiation intensifies by a factor of 4 compared to Earth's distance, driving surface temperatures on the nucleus well above the freezing point of water. Layered ices, some untouched since before recorded human history, begin to sublimate violently. The result is a pressure cooker effect, with jets of gas and dust erupting from weak spots and fractures, feeding the rapidly expanding coma and tail. Thermal stress at perihelion can crack open ancient comets, especially those returning after thousands of years spent in the deep freeze of the outer solar system. For C/2025 R2, the perihelion passage was both a trigger and a test of structural integrity. The comet's hydrogen envelope ballooned dramatically, signaling a spike in water production as solar ultraviolet light broke apart molecules streaming off the surface. Observers tracking the event noted the rapid growth of the coma, but the nucleus itself remained frustratingly shrouded. No resolved core was visible, just a bright, unresolved point at the heart of all that activity. With the sun's glare still masking direct observation, any sudden outburst or fragmentation event would go unrecorded until the comet emerged into darker skies. Perihelion isn't merely a milestone on an orbital path. It's a crucible that determines whether a comet survives intact, sheds significant fragments, or disintegrates entirely. For C/2025 R2, what happened during those critical hours near the sun would shape every unpredictable behavior that followed. The outbursts, the dust jets, and the potential for debris to scatter along its path. The real story of this visitor's volatility began the precise moment it crossed the perihelion line. On October 20th, 2025, C/2025 R2 will pass just 0.2606 astronomical units from Earth, roughly 39 million kilometers, or approximately 101 times the distance to the Moon. For a comet of this size and brightness, that's not simply close. It's a statistical outlier, the kind of flyby that happens once in centuries, not decades. But proximity alone doesn't tell the complete story. The minimum orbit intersection distance, or MOID, measures the smallest gap between Earth's orbit and the comet's own path. For SWAN, that MOID sits at 0.048 astronomical units, about 7.2 million kilometers. In cosmic terms, that qualifies as a near miss. It falls well within the zone that planetary defense teams use to flag potentially hazardous objects, even when the actual risk of collision is 0 for this particular pass. These numbers demand proper context. Mars at its closest approach comes within about 56 million kilometers of Earth. SWAN's flyby slices inside that distance, threading the gap between our planet and the orbits of our nearest neighbors. For comparison, the heavily publicized interstellar comet 3 I/Atlas never approaches closer than 1.8 astronomical units, over 270 million kilometers. SWAN's approach is more than 6 times nearer, and it's occurring during the same week. The ticking clock isn't about impact risk. It's about what can be learned and what might be missed during these few critical days of closest passage. With the comet's trajectory now established, the real urgency stems from its behavior. Outbursts, jets, and the potential for unseen fragments all become exponentially more critical as the distance shrinks. The MOID isn't just a number on an astronomical chart. It's a dividing line between a harmless flyby and a debris stream that could sweep through Earth's immediate neighborhood. Every kilometer matters in this equation. As October 20th approaches, astronomers are racing against time to collect every possible data point. The window for high-resolution imaging, for tracking sudden changes in brightness, and for mapping the dust environment is narrow and closing fast. Once SWAN recedes, the opportunity to study a long-period comet at this range won't return anytime soon. The clock is running, and the stakes ride entirely on how much information can be captured before the moment passes. Late September brought a shock that no model could have predicted. Comet C/2025 R2's brightness, which had been tracking a slow decline after perihelion, suddenly surged by more than a full magnitude in less than half a day. Observers in the southern hemisphere logged the dramatic jump first. What had been a faint smudge in wide-field images now rivaled the dimmest stars visible to the naked eye under dark skies. The comet's coma, already expansive, took on a vivid green cast, a telltale signature of C2 and CN molecules fluorescing under intense solar ultraviolet radiation. That distinctive color, familiar to veteran comet watchers, signaled intense molecular activity, a chemical flare-up as buried ices vaporized and rushed outward in tremendous volumes. Jets of dust and gas began fanning out from the core, carving transient arcs and streaks across the coma. The geometry of these jets shifted hour by hour, hinting at a spinning, possibly tumbling nucleus beneath the haze. Yet no telescope, not even the largest instruments on Earth, could resolve the core itself. The nucleus remained an unresolved pinpoint, masked by the glare of its own violent outgassing. Every attempt to detect a fragment, some secondary shard or companion piece, came up empty. If the late September outburst had cracked the nucleus open, the evidence remained buried in the dust cloud, invisible to all but the most sensitive instruments available. The unpredictability extended to the comet's light curve. Forecasts that had confidently placed Swan at magnitude 6 by October were overtaken by reality. The comet hovered erratically between magnitude 6 and 7, with wild swings recorded each night. Amateur astronomers debated whether they were witnessing fresh outbursts or simply the play of sunlight on previously ejected dust. The truth was sobering. No one could say for certain. Dynamically old comets like this one carry invisible scars from previous solar encounters, fractures, depleted reservoirs, pockets of volatile ices waiting for precisely the right moment to erupt. Each outburst rewrote the script entirely, and every spike in brightness raised the unsettling specter of fragmentation. The green coma, the erratic jets, the persistently unresolved nucleus, all point to a body in flux, its future behavior impossible to pin down with any confidence. For those tasked with tracking potential hazards, this represents a nightmare scenario. A large, highly active comet passing close to Earth with documented history of unpredictable outbursts, and no clear indication of structural integrity. The only certainty is uncertainty itself. And with every new image captured, the question grows sharper and more urgent. What, if anything, is hiding inside that cloud of dust and light? C/2025 R2's orbit reads like a cosmic warning, label written in the language of mathematics. Its path is stretched to the extreme edge, an eccentricity of nearly 0.999, an orbital period spanning over 22,000 years, and an inclination of just 4.5 degrees above Earth's orbital plane. That geometry is anything but random chance. Most long-period comets slice into the inner solar system at steep angles, spending only hours or days near the ecliptic plane before vanishing back into the deep outer reaches. Swan, by stark contrast, lingers in Earth's lane for weeks, crossing the same celestial highway where planets, satellites, and spacecraft travel. The statistical odds of such a massive, active body threading this particular corridor are extraordinarily slim, but the consequences ripple far beyond the raw numbers. Every outburst, every jet of escaping gas, acts like a miniature thruster on the nucleus. The physics is relentless and unforgiving. Sunlight pounds the surface, ices vaporize explosively, and jets erupt in seemingly random directions, pushing both dust and the core itself off their predicted paths. For a comet this active, the non-gravitational forces aren't just a minor footnote in calculations. They're a genuine wild card. Since perihelion, astrometric fits reveal a drift of approximately 1,000 kilometers from the expected trajectory, a direct imprint of outgassing thrust affecting the comet's motion. For smaller fragments, the effect becomes even more pronounced. Radiation pressure and gas drag can fling millimeter to meter scale debris onto wildly diverging tracks, seeding a diffuse stream that stretches along and away from the comet's primary path. These particles don't simply vanish into space. Over days and weeks, they spiral outward, forming a broad ribbon of dust and microfragments extending across millions of kilometers. Earth's orbit sweeps through this general region every year as part of its natural circuit around the Sun. But in 2025, the alignment is uncomfortably close to optimal for intersection. Even a diluted stream packed with particles too small to see from Earth can dramatically spike the background rate of meteoroids entering near-Earth space. For spacecraft operating in low Earth orbit, a few extra impacts per square meter can mean degraded solar panels, pitted sensors, compromised instruments, or in rare cases catastrophic failure. The risk isn't a sensationalized Hollywood impact scenario. It's the silent, statistical threat of elevated micrometeoroid flux, invisible until something critical stops working without warning. Historical analogs demonstrate how rapidly the space environment can change. Comet 73P/Schwarzmann-Watchman 3 shattered during a close approach in the 1990s, and its debris field peppered Earth's atmosphere with meteors for years afterward. Swan hasn't visibly split, at least not yet, but its erratic outgassing patterns and persistently unresolved nucleus keep that possibility firmly on the table. Each new jet, each unmodeled drift in position, serves as a reminder that the physics of comets doesn't end with calculating their orbit. It extends every fragment, every grain of dust, and every spacecraft potentially caught in the crossfire. The question now transcends simply tracking where the nucleus will go. It's about determining where its debris will spread and assessing how ready we are to detect it coming. October 2025 delivers a sky so crowded that even seasoned professional astronomers find it challenging to keep their observational priorities straight. Comet C/2025 R2 is far from the only comet lighting up brightness charts and social media feeds. C/2025 A3, better known as Comet Lemon, is steadily climbing in brightness, promising a spectacular binocular show of its own just as Swan reaches its closest approach to Earth. Simultaneously, the annual Orionid meteor shower peaks on the night of October 21st, sending brilliant streaks of debris from Comet Halley across pre-dawn skies worldwide. For the general public, it's an unprecedented celestial festival. 2 prominent comets visible during the same week, meteors flashing overhead with regularity, headlines overflowing with superlatives and cosmic wonder. But for those specifically tasked with monitoring genuine risks to Earth and orbital infrastructure, this convergence presents a troubling double-edged sword. The spectacle undeniably draws public eyes upward and generates valuable interest in astronomy. However, it also inevitably splits attention and resources. Outreach campaigns naturally focus on where to look in the sky and what to photograph for social media, while the subtler hazards, debris streams, fragment drift patterns, spacecraft exposure risks, tend to fade into background noise. Media coverage gravitates toward the visual and the immediate, not the statistical and the delayed. In a week densely packed with competing cosmic attractions, the challenge extends beyond simply seeing what's out there in the sky. It's about maintaining focus on which potential threats demand sustained vigilance, and which are merely beautiful distractions. The official discovery of C/2025 R2 triggered the standard international reporting chain. Minor Planet Center, then JPL Horizons, then the Center for Near-Earth Object Studies. Each critical step in this pipeline relies fundamentally on accurate data from the previous step, and every link harbors its own potential friction points and failure modes. The Minor Planet Center collects initial astrometry, position measurements, often within a day of confirmation. But for comets like Swan, that initial data starts thin and incomplete. Just a handful of post-Swan detections existed, all obtained after perihelion, with a nucleus still completely unresolved in images. JPL Horizons computes preliminary orbits using available observations, but with a short observation arc spanning limited sky positions, uncertainty balloons rapidly. By October 13th, orbital fit still depended on merely 3 weeks of tracking data and non-gravitational forces. Outgassing effects, asymmetric jets, subtle gravitational nudges, can push the predicted path by thousands of kilometers over time. The Center for Near-Earth Object Studies, serving as the endpoint for formal risk assessment, doesn't even open a detailed case file unless the initial numbers suggest a credible impact threat within defined parameters. For long-period comets specifically, the operational policy remains largely hands-off unless clear danger emerges. That policy choice leaves notable gaps in real-time alerting capabilities and comprehensive risk modeling, particularly when dramatic outbursts or sudden brightness jumps force rush manual review by limited staff. Each orbital update requires careful human oversight, not merely for numerical accuracy, but to identify the unpredictable anomalies that automated systems might miss. With aging instruments like SOHO Swan cameras showing calibration drift after decades in space, the pipeline faces genuine single-point failure risks. One detector, now decades old, stands solitary watch over the sun's dangerous blind side. The system appears robust on organizational charts, but in actual practice, late discoveries like Swan reveal just how much depends on luck, precise timing, and a small handful of overworked, dedicated observers. Small asteroids possess an unsettling way of slipping through even our best detection nets. In 2008, asteroid 2008 TC3 was spotted just 19 hours before it burned up spectacularly over Sudan, providing the first predicted asteroid impact in history. 5 years later, 2013 AA entered Earth's atmosphere with barely any advance warning at all. Even as recently as 2019, asteroid 2019 MO was detected only hours before it exploded in a fireball south of Puerto Rico, caught by chance observations. The lesson these cases teach is brutally simple. Approach angle and solar glare can erase days or even weeks of potential warning time, regardless of how technologically advanced our survey systems become. Comets introduce yet another layer of fundamental unpredictability to this equation. In the 1990s, Comet 73P/Schwarzmann-Watchman 3 broke apart dramatically during a close approach to the Sun, scattering fragments in dense dust clouds that peppered Earth skies with meteor displays for years afterward. The breakup was unexpected and created debris hazards that persisted long after the parent body had moved on. What all these historical cases share is a common vulnerability. Objects discovered late in their approach, or bodies that fragment unexpectedly, leave precious little time for any meaningful response. The operational checklist for addressing these scenarios has become painfully clear through hard experience. Update orbital predictions daily as new observational data arrives from global telescope networks. Push aggressively for high-resolution imaging campaigns to detect fragments as early as physically possible. Coordinate wide-field monitoring specifically for dust trails and potential meteoroid streams. Establish protocols to share real-time satellite impact logs and meteor radar data across international boundaries. Invest substantially in sunward-facing space telescopes, not merely expanded ground-based surveys with the same blind spots. And perhaps most critically, build accessible public dashboards that keep genuine risk factors visible and quantified, not just the spectacular visual elements. Each late discovery serves as another stark reminder. Constant vigilance represents our only viable defense when the sky's inherent blind spots remain this dangerously wide. On September 11, 2025, Comet C/2025 R2, designated Swan after its detecting instrument, was discovered just 1 day before its closest approach to the Sun, successfully evading every ground-based survey system due to the notorious Hollich blind zone. Unlike the widely discussed and heavily publicized 3I/Atlas, Swan will pass within 0.2606 astronomical units, approximately 39 million kilometers, of Earth on October 20th, 2025, making it one of the closest comet approaches in modern astronomical records. Extensive archival data and preliminary trajectory analysis confirm no direct impact threat to Earth during this passage. However, the extremely late discovery combined with documented unpredictable outburst activity underline a critical systemic blind spot in our current detection pipeline. Past cases like 2008 TC3 and 2013 AA demonstrate conclusively that potentially hazardous objects can appear with shockingly little advance warning, and the dramatic 73P comet breakup remains a perpetual cautionary example for real-world fragmentation risk. Today, the authentic risk doesn't stem from the comet's nucleus itself, but rather from the fundamental limits of our monitoring capabilities, especially for objects arriving from solar directions. As the near-Earth environment grows increasingly crowded with both natural and human-made objects, the need for frequent observational updates, targeted follow-up observations, and substantial investment in space-based sun-facing telescope systems remains urgently pressing. The story of C/2025 R2 Swan stands as a humbling reminder that the next cosmic surprise may already be on its way toward us at this very moment. Hidden in the sun's blinding glare, silently waiting to be seen. The question isn't whether another such object will appear. It's whether we'll spot it in time. At 11:47 p.m. Universal Time Coordinated, amateur astronomer Sarah Chin was wrapping up her observation session from her backyard in rural New Zealand when she noticed something wrong with her images of C/2025 R2. The comet's coma, which should have appeared as a smooth, diffuse glow, showed a distinct elongation, almost as if something had been ejected from the nucleus hours earlier. She immediately uploaded her images to the Comet Observation Database, flagging them as urgent. Within 20 minutes, 3 other observers in Australia and Chile confirmed the anomaly. The comet's brightness had jumped again, this time by 1.8 magnitudes in just 6 hours. But this surge looked different. The coma wasn't expanding evenly. It was developing a pronounced asymmetry, with one side substantially brighter and more structured than the other. At the Minor Planet Center, Dr. James Whitlock received the automated alert at 2:14 a.m. What he saw in compiled images made his stomach drop. The asymmetry wasn't random outgassing. It was the unmistakable signature of a fragment separation event, and it had happened sometime in the previous 12 hours, completely unobserved. By dawn on October 20th, emergency observation campaigns were underway at every major observatory in the Southern Hemisphere. High-resolution imaging from the Gemini South Telescope finally revealed what everyone had feared. C/2025 R2 had split. A secondary fragment, designated Swan B, had separated from the main nucleus during an explosive outburst on October 18th, over 36 hours earlier. The fragment wasn't large, perhaps 200 meters across, but it was moving. Non-gravitational forces from its own outgassing had pushed it onto a slightly divergent trajectory. More critically, the breakup had occurred at the worst possible moment in the comet's orbit, just as it was making its closest approach to Earth. JPL Horizons ran the numbers 3 times, each calculation confirming what no one wanted to see. The fragment trajectory uncertainty was massive, a consequence of the late detection and violent birth. The probability cloud stretched across millions of kilometers, but its central path intersected a region of space that would be occupied by over 40 operational satellites within the next 18 hours. Most alarming was the debris trail. Radar observations from the Arecibo Successor Facility in Puerto Rico detected a dense cloud of centimeter to meter scale fragments extending along Swan B's path, a shotgun blast of material moving at 42 kilometers per second relative to Earth. The International Space Station received the first priority alert at 6 a.m. Universal Time Coordinated. Mission Control initiated emergency protocols, calculating whether a debris avoidance maneuver was necessary. The answer was both reassuring and terrifying. The ISS would miss the densest part of the debris field by approximately 400 kilometers, a comfortable margin by orbital standards, but far closer than anyone wanted. For the commercial satellite operators, the news was worse. 3 Starlink satellites occupied orbits that intersected the debris field's probable path. SpaceX began emergency maneuvers to lower their altitudes, but the process would take hours, and the debris cloud was spreading. At 2:31 p.m. Universal Time Coordinated, the James Webb Space Telescope, in its orbit at the L2 Lagrange point well beyond Earth's orbit, captured the most detailed image yet of Swan B. The fragment was tumbling violently, venting gas in irregular bursts that changed its trajectory by several kilometers every hour. Predicting its exact path had become a game of probability, not certainty. Ground-based meteor radar stations began reporting anomalous activity at 4 p.m. Universal Time Coordinated. The background meteoroid flux, the steady rain of cosmic dust that Earth encounters constantly, had tripled in less than an hour. It wasn't catastrophic, but it was measurable and it was growing. The moment of closest approach arrived not with a bang, but with a cascade of small, disturbing events that unfolded across 3 hours. At 8:17 p.m. Universal Time Coordinated, C/2025 R2's main nucleus passed 38.97 million kilometers from Earth, slightly closer than predicted 39 million, a consequence of those non-gravitational forces that had played trajectory predictions from beginning. Amateur astronomers worldwide captured stunning images. The comet blazed at magnitude 4.8, easily visible to the naked eye under dark skies, its green coma spanning 2 degrees of sky, 4 times the width of the full moon. Social media erupted with photographs and time-lapse. For millions of people, it was the astronomical event of the decade, but in mission control centers across the globe, the mood was tense. At 8:43 p.m., one of SpaceX's maneuvering Starlink satellites reported a sudden loss of telemetry. 27 seconds later, the signal returned, showing degraded solar panel output, consistent with hypervelocity impact from a small particle. The satellite was functional but wounded. At 9:15 p.m., a European weather satellite in sun-synchronous orbit registered an impact on one of its outer panels. Damage assessment showed a 3 mm penetration, significant but not mission-ending. At 9:52 p.m., Meteor cameras in Japan, South Korea, and the Philippines simultaneously recorded an unprecedented burst of activity. Over 40 bright meteors appeared in just 12 minutes, all radiating from the same point in the sky, the radiant that corresponded to Swan B's debris field entering Earth's upper atmosphere. The fragment itself, Swan B, passed at 10:04 p.m. Universal Time Coordinated. Its closest approach to Earth measured at 2.1 million kilometers. In astronomical terms, a clean miss, but its debris trail extended millions of kilometers in every direction, and Earth had just flown through the outer fringes.